Okay, I guess we're gonna start now. My name is Carl Marietta, and I work with FEB Energy. We're a district energy heating and cooling consultant, and we've put together these series of STEAM education seminars for the people at the utility. We did that already a week or so ago, and then we did one earlier today for contractors or vendors in the area, and then this is the public one. So this is the first one, and obviously I think it's helpful if you don't you don't see something that you wanted to see, or you had more questions about something you wanted us to spend more detail on. You can let the guys know from New Ulm Public Utilities, and the next time we do it, we will try to add those things in and improve it. So it should last approximately an hour. I have a number of videos that we're going to look at, and these are the screens, so you might want to get yourself in position to, if you're seeing them fine, that's good. Okay, so we're going to basically cover two kind of main topics here today. One is just basic concepts of steam heating, which you may be familiar with it and you may not, so you'll have to just bear with it if it's very understandable already, but it kind of brings you up to, because there's no use talking about some of the other things that we want to talk about if you don't have that least kind of understanding of how steam works inside a building to heat the building. And then we're going to talk about the control of steam radiator heating systems, how to control them, how to make them work good inside the building. So those are the two topics we're going to cover today, and we'll get started on that. In the basic concepts, we're going to talk about how the heat of steam is utilized. We're going to talk about condensate, what it is, why you have to get rid of it. We're going to talk a little bit about air and why you don't want air inside mixed with the steam, and corrosion, how that can really wreck your systems, and how to get rid of condensate, air, and non-condensable gases. That's very important. And that all done by a steam trap. And a steam trap is a very important device in a steam heating system. We're going to talk something about steam traps and show you some videos on how they work, and we're going to talk about why they're important. First I'm going to show you a short 10-minute video on steam basics.
Welcome to today's lesson, Steam Basics. Click the Start button to begin. In this course, you will learn about steam and identify what steam is. Learn how the energy of steam is used and identify the many properties of steam. Please allow at least 30 minutes of your time to complete this course. Taking full advantage of the steam utility depends on a thorough understanding of its potential and properties. The more you know, the greater the benefit you'll enjoy. To say it another way, the more you know about steam and how to control and use it, the greater the return on the investment in a steam system. Our journey towards understanding steam begins. Click play to continue. Steam is an odorless, colorless gas that is created when water is heated to its boiling point and changes state or vaporizes from a liquid to a gas. When heat energy is removed from steam, it loses its ability to retain a gaseous state and condenses back into a liquid. The resulting liquid is called condensate. The process of condensation happens quickly. The temperature at which condensation takes place is known as the dew point. There are various forms of condensate that are sometimes incorrectly referred to as steam. These forms, however, lack the molecular makeup of a gas. Some examples of these are the mist you see rising above relatively warm water on a cool day is in fact water vapor condensing in the air. The droplets on your bathroom mirror are formed when water condenses out of the relatively warm air onto the cooler surface of the mirror. Click play to continue. Let's take a closer look at steam's practical uses. Click play to continue. We use steam in our everyday life in many different ways. From the plastic and vinyl components of our automobiles, to the paints and stains we use on our homes, to the preparation and presentation of the food we eat, we use steam to make our lives more comfortable and convenient. Fuel is consumed to heat the water that becomes steam. The gas has value. It contains valuable and useful heat that can be used in a variety of purposes. In fact, steam is used in the manufacturing of more than 80% of the products produced by industry. Steam has several physical properties that make it particularly suitable and economically advantageous for these industrial purposes. Click play to continue. Let's examine the steam loop. Click play to continue. Most industrial steam systems are closed systems. When water vaporizes to become steam in the boiler, the expansion pressurizes the system. Steam is forced out of the boiler by its own pressure and is carried by piping to whatever devices are to be employed for heating or processing. The pressure changes within the system provide transportation for the steam and also affects its physical properties. It is helpful to think of the typical steam system as a loop with 4 distinct sections. The first is generation. During this stage, in the boiler, heat is applied to water to raise its temperature. After the water has vaporized, the resulting steam moves into the second stage of the steam loop, distribution. This is simply the movement of the steam within a closed system to its point of use. The use, whatever that happens to be, is called heat transfer. This is the third stage. In the heat transfer portion of the steam loop, the heat of the steam is put to work doing countless jobs. As the steam gives up its heat through heat transfer or use, it condenses or changes its state, this time from a gas back into a liquid. This is called condensate. We'll learn later why it's very important to drain condensate from a steam system as quickly as possible. This is the job of a simple device called a steam trap. The fourth and final section of the steam loop is condensate return. Since condensate has already been through the steam system, it will take far less heat and fuel to turn it back into steam than it would to make steam of an equal quantity of cold water. That's why a growing number of steam users return the condensate back to the boiler where the whole process starts over. Hence, the concept of the steam loop. A discussion of temperature and heat is essential to an explanation of how water becomes steam. Click play to continue. Temperature is a measurement of the molecular motion within a substance. Water in a teapot, for example. Faster moving molecules result in higher temperature. We measure temperature on a thermometer, which sets the freezing point of water at 32 degrees Fahrenheit and boiling point of water at 212 degrees Fahrenheit at sea level. Heat is a measurement of the movement or transfer of energy from a body with a higher temperature to a body with a lower temperature. We measure heat in British thermal units, BTU or kilojoule. 1 BTU is the amount of heat required to raise the temperature of 1 pound of water 1 degree Fahrenheit. In SI units, the kilojoule is equal to a kilowatt second. Water can absorb only so much heat. This is called sensible heat because it produces a temperature change that can be measured. The amount of sensible heat that is required to raise the temperature of water from freezing to boiling is called the heat of the saturated liquid. At sea level, atmospheric pressure is about 180 BTU per pound of water. Adding more heat to water has no effect on temperature. Instead, it causes the water to change state, or vaporize, from a liquid to a gas. About 970 BTU of additional heat is required to vaporize 1 pound of water into 1 pound of steam. This is called latent heat because it cannot be measured by a thermometer. Water is made up of hydrogen and oxygen atoms. At lower temperatures, these molecules are loosely bonded to each other. When heat is transferred to the water, the molecules begin to vibrate and the temperature starts to rise. As the heat increases, the molecules vibrate more and more until the bond holding them together is severely weakened. When sufficient heat has been transferred to the water to break the bonds, the molecules explode apart, creating steam. After the steam has been transported to the heat exchanger, it gives up its latent heat to raise the temperature of some product or to power some operation. As the steam gives up its latent heat to the work effort, it condenses back into water. Click play to continue. Heat transfer takes place in three ways: conduction, convection, and radiation. Let's take a closer look. Click play to continue. Conduction is the form of heat transfer that takes place within a solid. Conduction causes the handle of a cast iron frying pan to be nearly as hot as the bottom. Conduction occurs within a solid or between two solids in contact with each other. It is generally believed that conduction occurs on the atomic level, much as the conduction of electricity takes place. Free electrons transport thermal energy from molecule to molecule away from the heat source. Click play to continue. Convection is the form of heat transfer that takes place within gases or liquids or between solids and liquids or gases. Convection causes the air from your heating system to be distributed throughout the room. Convection also requires physical contact. It takes place because of the difference in density in fluids as they are heated and cooled. Liquids or gases are heated and become less dense and rise. As they cool, they become denser and fall. In a system, this cycle of movement is called a convection current. Click play to continue. Radiation is the form of heat transfer that takes place between two bodies that aren't in physical contact. Radiation causes sunburns that many of us get when we've stayed out in the sun for too long. Radiation is the only form of heat transfer that requires no physical contact. While we do know that it occurs because of electromagnetic radiation, usually in the infrared band, much of our understanding of it is still theoretical. We do know that it can take place between two bodies separated by a vacuum and is partially explained by wave theory and quantum mechanics. Click play to continue. Often, heat transfer occurs as a combination of the methods we've discussed. For example, fire heats a frying pan by convection. The heat is then transferred from one side of the frying pan to the other by conduction. The egg in the pan is cooked by conduction heating. Click play to continue. Steam is complex. When we break down its properties and begin to understand them, we become...
So that's just a basic introduction to steam. Now, just to put it in a little bit terminology that you might understand better, like you are billed for like 1,000 pounds of steam, for example. As you saw from that video, 1 pound of steam, when it gives up its latent heat, it gives up 970 BTUs. So 1 pound of steam roughly is equal to 1,000 BTUs. So 1,000 pounds of steam is equal to roughly 1 million BTUs. So sometimes you'll see conversions like how many BTUs are in a kilowatt hour. There's 3,413 BTUs in a kilowatt hour. So you can, and there's so many BTUs in natural gas and other kinds of fuel. So if you want to understand, how much fuel you're actually using inside the building, you can convert your pounds of steam to BTUs, and then you can see how it converts to other kinds of energy measurements. Also, like if you think about the steam radiator, and we'll talk about this more as we go along, but that steam radiator, in order for it to function properly, the steam has to condense inside that radiator. Because if it's just flowing through the radiator will be hot, but it's not going to give much heat off. It's only going to give the radiation heat that comes off the steam. But if it gives up the latent heat, that 970 BTUs per pound, that's where you really get the heating energy out of the steam radiator. So we'll talk a little bit more about that as we go on. Now, condensate, as the video showed, is something that happens to steam after it condenses, and you have to get rid of it. I mean, you want to clear it out of the system for a number of different reasons. So you don't want it lying in the bottom of any steam lines in your building, in the distribution system of the plant or the streets, because steam running over top of it will sometimes create waves, and I'll show you a video of what that looks like. And it gets behind the condensate and it starts to push it, and if it creates a big enough wave, the condensate will actually block the pipe, and then that shoots that slug of water down the pipeline, and whatever it hits, a corner, a valve, or any kind of restriction, it can be really destructive. And sometimes when it's not that destructive, you can hear it. Like if you hear your radiators like clanging or something like that, that's due to water hammer. It's due to the steam pushing the condensate someplace and hitting something inside your system and making it bang like that. And that's something we want to avoid, because over time that kind of water hammer will destroy things. Also, and so let me show you this short video of what it kind of...
Water hammer. It's a familiar sound nearly everyone has heard. Shock can occur whenever steam and condensate flow in the same line, but at different velocities, such as in high-pressure condensate return lines. In biphase systems, the velocity of the steam is often 10 times the velocity of the liquid. If this gas flow causes condensate waves to rise and fill the pipe, a seal is formed with the pressure of the steam behind it. Since the steam cannot flow through the condensate seal, pressure drops on the downstream side. The condensate seal now becomes a piston that is accelerated downstream by virtue of this pressure differential. As it is driven downstream, the piston picks up more liquid that is added to the existing mass of the slug, and velocity increases. This is differential shock. If the slug gains high enough momentum and is then required to change direction at a T or elbow, or is stopped by a valve, great damage can be done. In the demo lab at Armstrong International, we have assembled a fixture to illustrate the problem. We use this 20-foot, 2-inch diameter glass pipe to act as a condensate return line. The pipe is pitched 1/4 inch in 10 feet to provide gravity flow. Flowing through the pipe, we have cold water. In addition to water, we can also have compressed air flowing in the system to simulate flash steam flowing across the top of the condensate by virtue of differential pressure. One flow meter constantly measures the flow rate of the water. Another flow meter continuously monitors the flow rate of the compressed air. As you can see, we now have 1,500 pounds per hour of water flowing in our glass pipe, and no compressed air. Under this condition, our pipe is approximately half filled with water. As we increase the flow rate of water in our pipe to 2,000 pounds per hour, the depth of the water increases to 5/8. We now introduced compressed air into the system to simulate flash steam, with a flow rate of about 200 standard cubic feet per hour, and the depth of the water recedes. We are increasing the speed of the water flowing through the pipe by virtue of the velocity of the gas flowing across its surface. Observe now as the compressed airflow increases. The waves formed on the surface of the condensate become higher. Further increasing the airflow causes the waves to block off more of the cross-section of the piping until a seal is formed, completely closing off the pipe. A slug of condensate is accelerated downstream by the pressure differential, becoming a piston that gains in mass and velocity as it travels. The proper sizing and pitching of condensate lines are the only means of guarding against this type of problem.
Okay, so that was just a nice visual idea of what that water hammer looks like. So when you hear that banging, that's basically a slug of water that steam is pushing through the system, and it's hitting something. It's hitting an elbow, or it's hitting a valve or something and really banging, or hitting the radiator and banging. So now we're going to talk a little bit about steam traps, because they're the most important kind of device that you have. It's the device that has a moving part. It's probably the only device that has a moving part in your steam system. And it's really important that these steam traps work properly. So I have a couple there's a short video, 2 or 3 minutes for each one of these 4 major types of steam traps. And I'm just going to show you so you get an appreciation of how each one works.
The IV steam trap is a continuous drainage, intermittent discharge device that operates on the mechanical principle. The heart of the inverted bucket trap is this bucket. In the inverted position, it acts as an open float. It is capable of functioning under very high pressures because the same operating pressure is exerted both inside and outside the bucket. A small orifice called a bucket vent is located at the top of the bucket to ensure that non-condensable gases cannot be trapped inside the bucket. Steam, air, and condensate enter the trap through an inlet tube beneath the bucket. Air and condensate are discharged through an orifice at the top of the trap. At the orifice is a valve that is linked by a lever to the top of the bucket so that the valve is closed when the bucket is in the up position. The body of the trap is a cylinder which contains the bucket. During proper operation, this cylinder is always filled with condensate to a level above the top of the bucket. This condensate provides a constant water seal above and around the bucket, preventing live steam from escaping from under the bucket. Finally, in the cap of the body is a space above the water seal where any non-condensable gases which have passed through the bucket vent will collect while the valve is closed. Incoming steam is trapped between the top of the bucket and the water seal below. When approximately 2/3 of the volume of the bucket is filled with steam, the bucket becomes buoyant and floats to a point where the valve is pushed toward the orifice by the bucket clip extension. The higher condensate velocity near the orifice propels the valve into the seat, where it is sealed and held shut by differential pressure. Radiation causes the steam inside the bucket to cool and condense. If the condensed steam is replaced by more steam, the bucket remains buoyant and the valve closed. However, when enough steam has been condensed by radiation and is displaced by entering condensate so that only 1/3 of the bucket volume contains steam, the bucket loses buoyancy. As more steam condenses, the bucket becomes heavy enough to pull the valve off its seat. With the discharge valve open, condensate flows down around the bottom of the bucket and out through the discharge port. Air too rises to the top of the bucket, where it flows through the bucket vent and water seal, accumulating at the top of the trap. When the valve opens, the air is pushed out of the trap ahead of the condensate.
So there's two, you'll see this again as we see the other traps. The main thing that the trap wants to do is get rid of the condensate without letting the steam go through, and also get rid of non-condensable air like oxygen or CO2, because those can damage the system, as we'll discuss in a little bit. So each one of these traps, basically they're slightly different, but they all do the same.
Float and thermostatic traps offer a combination of mechanical and thermostatic operation. A closed float is used to sense the density difference between a gas and a liquid. The float is attached to one end of a lever which pivots inside the trap. At the opposite end of this lever is a valve that is seated when the float is at rest. Condensate enters through the inlet near the top of the trap and raises the float, opening the valve. The condensate drains from the trap through the outlet near the bottom, leaving a condensate seal between the inlet and the valve. Above this seal, near the top of the trap, is a thermostatic bellows. The bellows responds to temperature change. When this space is filled with hot steam, the thermostatic valve is closed. Non-condensables, such as air, mix with the steam and cool the space near the top of the trap. When the bellows element cools sufficiently, the thermostatic valve will open and vent these gases into a passage leading to the trap discharge. At startup, the float is down, the float valve closed, and the thermostatic valve wide open. Non-condensable gases reaching the trap are immediately vented through the thermostatic valve at the top of the trap. Condensate collects at the bottom of the trap until the float begins to rise, opening the float valve. The float valve normally drains continuously from this point. The condensate level in the trap lowers and raises the float height, thus modulating the discharge flow. When steam reaches the trap, it collects above the condensate level and heats the thermostatic element, closing its valve. Hereafter, the thermostatic valve will open intermittently to vent mixtures of non-condensables and steam. Should the trap become waterlogged, cooled condensate would open this valve and drain to the discharge line.
This is a thermodynamic trap called a disk trap.
The disk trap is a thermodynamic trap. These traps are operated by the energy released when the condensate changes state, or flashes between the disk and the seat. The disk trap contains only one moving part, the controlled disk itself. When the trap is closed, the disk is on the seat, sealing both the inlet and the outlet orifices. The area containing the disk is called the control chamber. It is a relatively large volume space with restricted inlet and outlet ports. It is the change of state which occurs here that normally controls the opening and closing of the disk trap. On startup, condensate at the inlet port pushes the disk off the seat and flows freely to the outlet port. Condensate passing into the trap drops in pressure. If the condensate temperature is sufficiently high to have reached the saturation for this reduced pressure, some of the condensate re-evaporates or flashes back into steam. Since steam occupies a much greater volume than condensate, flow velocity increases between the disk and seat, resulting in a pressure reduction in this area. At the same time, steam and some condensate collects on the side of the disk opposite the seat, and pressure here rises. The resulting differential pressure across the disk creates a force which snaps the disk onto the seat. The steam in the control chamber pushes on the total area of the disk, while the inlet and back pressures affect only the smaller areas of the inlet port and the discharge groove. This imbalance of force holds the trap shut. Heat radiating from the bonnet causes condensing in the control chamber, reducing the pressure above the disk. When the force above the disk is overcome by the forces below it, the disk is pushed off the seat, opening the trap and starting the next cycle. Since any gas, including air, causes the trap to close, some provision must be made to remove non-condensables from the control chamber. This is usually accomplished with a rough grind applied to the seating side of the disk, or a bleed passage machined between the control chamber and the outlet.
Okay, so now this last trap is very important for you, I think, more than maybe the others. This is the kind of trap that is on your radiator if you have a two-pipe system. It's called a thermostatic.
Hi, I'm Ron from Keystone Steam Supplies, and today we're going to talk about steam traps. First of all, what is a steam trap? There are many different types of steam traps and a variety of sizes and materials of construction, but at the core, a steam trap is a mechanical device used to manage the flow of steam. It behaves much like a traffic light at an intersection. If steam is present, it stops its flow into the return system until it's spent its energy and becomes condensate or hot water. Once this occurs, it allows the condensate to flow into the return piping system and make its way back to the boiler where, once again, it will become steam. The most common type of steam trap is a thermostatic trap. The thermostatic trap is a balanced pressure, temperature-based device, meaning that it responds to the difference in temperature, as between steam and hot water, or steam and air. It's most commonly found at the end of radiators in heating systems or after machinery in process work applications. The trap is available from multiple manufacturers in a vertical pattern, angle pattern, horizontal or straight pattern, combination angle horizontal pattern, or a 90-degree horizontal pattern, that is, a left or right turn. It can operate in steam pressures from vacuum to an excess of 300 psi. It can be made from brass, bronze, cast iron, stainless steel. As you can tell, there are many options available, and yet they all operate in exactly the same way. At the heart of any thermostatic steam trap is the bellows. Once again, the bellows can be made from any one of several different materials and in either single or in multiple convolution varieties. Inside of each bellows is a volatile liquid that reacts to its surroundings. Remember the traffic light? Well, when the bellows is surrounded by steam, the liquid inside of the bellows turns into steam, causing the bellows to expand. When the bellows expands, it causes the plug, which is attached to the bottom of the bellows, to close the opening in the trap seat, and thus stopping the flow of steam into the return piping system. Once that steam has expended its energy, whether it's to heat a radiator or turn a turbine, and condense into water, that water now surrounds the bellows, and the steam inside the bellows condenses into water, contracting the bellows. This backs the plug away from the seat and opens the orifice in the bottom of the trap, allowing the condensate to flow into the return piping system, and thus making its way back to the boiler, where once again it turns into steam and the cycle repeats. And that's how a thermostatic trap operates. As long as the system is in operation, it constantly monitors the flow, stopping the steam from escaping until it's given up its energy, and then letting the condensate go back to the boiler. The bellows is constantly flexing, opening and closing, and eventually it will rupture due to metal fatigue and need to be replaced. Keystone Steam Supplies is here to...
Okay, so that's the kind of trap that you have or should have on your radiator. And I think the one key point is it's a moving part. It doesn't last forever. It will fail. And when it fails, it may fail open. If it fails open, that means steam is just traveling through the radiator and right on into your condensate return system and condensing someplace where it does you absolutely no value. The whole concept of the steam trap is to stop live steam, force it to condense inside the radiator so that you get the maximum heat. So one thing you should take away is that it's very important that you have somebody check your radiator steam traps at least annually. That's a very important thing, because if they're failing, you're not getting the value of the steam that you're purchasing. As we see, the trap needs to do a number of different things. First of all, it doesn't want to, there's always some steam loss when the trap opens up, but you want to keep that to a minimal amount. You want a long life and dependable service from the steam trap. You want it to be corrosion resistant, because we'll discuss here in a minute, there's corrosive things that are going on inside of a steam system that it needs to fight. It needs to vent the air, and we'll talk about that in a minute, including CO2, which is when he talks about non-condensable gases, that's what he's talking about. And the operation has to operate against back pressure. That shouldn't be a problem so much for building heating systems. And it has to be freedom from dirt problems, because you will get dirt inside these systems. It comes from corrosion. Things flake off inside the pipe, and if it gets into certain kind of traps, can't handle dirt. This system, that kind of a trap, should be reasonably impervious to it. Just to emphasize the thing about evacuating the air, because there's a couple things that go on if you get air and mixed steam. An air and steam mixture has a lower temperature than pure steam. So if you've got air infiltrating into your steam system and you're not getting rid of it, then you won't get the same temperature out of the system that you want, that it was designed for. So it's very important to get the air out. And that's what the trap does. Also, if you don't get those non-condensables out, like CO2, CO2 comes in through the system. It's trained in the steam sometimes, And when it condenses and cools, it turns into carbonic acid. This is a highly corrosive acid that will eat out pipes and insides of things that you don't really want that to happen. So this is another reason why it's very important to have traps on the system that get the air out of the system, because you don't want that kind of corrosion going on. And oxygen is there. It's also because, especially in the condensate return system, it's a gravity system, so air is in there with the condensate, and those two things together combine for sometimes very corrosive situations. So you want to get that air out of there. Traps basically do two major things, as we're discussing. They get rid of the condensate because that could reduce the heat transfer. If you've got system where the condensate is laying in the radiator, you're not getting the full heat capacity out of that radiator. And they also can cause water hammer, as we discussed. They also get rid of air, and CO2, which can cause corrosion. So it's very important that you have traps on your system that are working properly. So, by the way, I mean, this is an open, I should have mentioned it before. If you have a question or you want to stop me, just go right ahead. It's very informal here. So now I want to talk a little bit about how do we control steam radiator heating systems? Because this is a known problem. You know, people have a lot of difficulty with it, but it can be made to work properly. The first question you have to ask yourself in the place where you live or work, do I have a one-pipe system or a two-pipe system? It's pretty, I mean, it's kind of explanatory, but if you have a one-pipe system, like this one on the left, you only have one pipe connecting the radiator, not two. And that is a one-pipe system. And the control of a one-pipe system is totally different from the control of a two-pipe system, which we'll get into in a minute. A two-pipe system, you have the steam valve coming up through and into your radiator, and then you have the discharge and a trap, and you have a condensate return line running off the radiator. That is a two-pipe system. And it's important to understand that the control of those are quite different. Does anybody know what kind of system they have in their building? Or okay, so you can go back home and look. There's only one pipe connecting the radiator. You have a one pipe. Two? You got two. So for a one-pipe system, the way to control one-pipe system is with controlling the air. And there's a manual ones, which I'm showing here, and there's automatic ones. The automatic ones are better than manual, and I think you can understand, but I'll explain it a little bit more. Basically, what the air valve does is when the steam tries to come up into the radiator, if that radiator is filled with air, and the air can't go anywhere, then no steam can enter the radiator. So you have an air valve on the radiator to release the air so that the steam can enter into the radiator and cause the radiator to act properly. Now, one of the things that you might experience or see is that radiators that are close to, if you have this situation, radiators that are close to the main piping get very hot and stay hot all the time, but radiators that are in the exterior parts of the building never get hot. That's because basically the interior radiators are hogging the steam. One way to control that is to put manual adjusted air valves on the interior radiators and basically close down the amount of air that can release. That allows only a certain amount of air to go into those and forces the steam out into the exterior radiator so that you get even heating throughout the whole building. Now, a better solution is to use an automatic adjusted air valve. That's basically the air valve with a thermostat on it. Now you can set the temperature for that particular radiator that would allow steam to enter the radiator. If the room is hot and the radiator is not going to open the air vent, that radiator is not going to get hot. And the rest of the steam is going to be forced out into the other parts of the building, exterior parts where the other radiators are. Now, one of the things that happens in a lot of these older buildings is that the amount of radiators that were put in back when the building was built was designed at that time. There was very little insulation in buildings. And if over the time people have insulated their buildings, and basically it's a good chance you have too much radiation capacity in your building. So one of the things you can do is you can experiment a little bit. You could put an automatic adjusting air valve on one radiator in a room and shut the other one off. And this also will keep that room from getting really, really hot and keep the other rooms or areas will get their share of the steam. And I know a building that we worked on, like a woman had lived in her apartment for 10 years and she had basically had electric resistance heaters up there because even though she had radiators, she never got any steam. We put these automatic adjustable air valves on, and she said for the first time in 10 years, her radiator got hot. And so it does make a difference. So it can really improve the value of these things. And as you can see here, the manual valves cost less than $30, and those are prices I just pulled off of Amazon. An automatic adjusted air valve costs less than $50. So you wouldn't want to put them on every radiator in the entire bit, but you could selectively put them. I would start by putting them in areas where you have too much heat, control that, and then force the steam out to the place where you're not getting any heat. Now in a two-pipe system, it's a completely different kind of a control system. Those radiators have to have traps in order to work. And the other way to control them is using a thermostatic radiator valve. The reason that they need a trap is that, and this is the thermostatic trap that you saw the presentation on basically. And those cost less than $60, but those are very important for a two-pipe system because the trap basically says to the radiator, if steam has come to the trap, then I want the trap is going to close. And it's going to hold the steam in the radiator until it condenses. Because then you're getting that full 970 BTUs out of the steam. If the trap, for example, wasn't working or you didn't have a trap, the steam will just flow through the radiator. The radiator will be hot to touch, but it doesn't give out any heat. It doesn't give out the kind of heat that you need to heat the building for what it was designed. The steam has to condense inside the radiator in order for you to get the heating that you want. The other thing, to prevent overheating in some areas and underheating in others, you can put a thermostatic radiator valve. They cost less than $50. Again, I would concentrate on putting them close to the places or from experience get too much heat. You can also shut off radiators along with this because you probably have too much radiator capacity in some of these older buildings. The valve costs less than $50 and it's thermostatically controlled. They even have a kind that you can mount them on the wall, like a wall thermostat. This is a simple one pictured here that's connected right to the radiator. You can set that for comfort in that room and basically it just shuts off steam to that radiator if the room is meeting the thermostatic requirement. Now we'll just talk a little bit about the troubleshooting of these systems in case you have problems, which is not unusual. In a one-pipe system, you want to make sure that the steam pipes that are running through the building are insulated to work properly. You have to be sure, remember that in a one-pipe system, the condensate is flowing back through the same line that brings the steam. It's very important that you make sure that the condensate can flow back through that system. For example, if you have a radiator, if the one pipe is here, and the radiator is slightly tilted over the time it sat on the floor, maybe the wood floor, it shifted a little bit. If that radiator is canted away from the one pipe, basically the condensate builds up inside the radiator and basically blocks the steam and doesn't allow the radiator to heat. You have to make sure that radiator drains the condensate back to the one-pipe system. So it needs to be slightly canted towards the one-pipe system so that the condensation that forms inside the radiator easily flows out of the radiator and back down the pipe. If you have a radiator that's just warm, it's full of condensate, it's not heating at all, you need to get a level out, put the level on top of the radiator, and raise the back one set of legs till you get a slight gravity drain, and you'll be surprised. That radiator will start to heat. And of course, if you have air valves already, you need to make sure that they're working properly. In a two-pipe system, if you have that kind of a system, it's very important that you check for failed radiator traps. You saw the radiator trap, it's got those little bellows inside. Those things fail. I don't know exactly what the life of them, and it depends on the use of the system. But they're fairly simple to check to see if they're operating. We had earlier classes with the contractors here in town and showed them some methodologies for easily checking those things. So you could just have somebody come in annually. It's like annual maintenance of anything, a furnace or whatever. You can have them come in, check to make sure that those steam traps on the radiators are working properly, and also if there's thermostatic valves, that those thermostatic valves are also working properly. You don't, if somebody suggests that you put air valves on individual radiators on a two-pipe system, this is not a good solution. There should be some place on the main piping system where you have a thermostatic air vent that vents the air. Because when you shut the system down, the steam condenses and it fills with air. You have to get rid of that air in order for the steam to get back into the system. The best way to do that is to find some place at the upper level of the steam distribution system and put in a thermostatic air vent. When the steam is turned on, that vent is open. The steam will flow through the distribution system, and when the steam hits that air vent up at the top, it closes, holding the steam in the system. And then, of course, it can feed the radiators and do the proper heating. So that's an important thing. You might have clogged condensate piping, because as we talked about, there's corrosion, older systems, the metal flakes off inside, it can block. If the condensate is blocked, it'll back up behind the into the radiator and basically shut the radiator off because it'll be blocked. If condensate can't get out of the radiator, it just floods until there's no capacity left. And of course, you have to check for the thermostatic radiator valves. If you've got those kind of radiator valves, you need to check them, make sure they're operating properly. So this kind of brings us to the end of this small presentation, but I believe that Derek wants to introduce you to the rebate program that they have.
All right. Hello, thank you everybody for coming. I know it's kind of a late evening for everybody that's had their shop open or wants to get home, but my name is Derek Nelson. I'm the Energy Services Representative for the Public Utilities. And I just kind of wanted to bring to the attention to anybody that owns the steam system or pays the steam bill that the Public Utilities does have a rebate for many things that can be done on a steam system, from getting the pipes worked on to traps, which was just talked about, which are pretty important, all sorts of valves. So if there's any work that possibly could be done, my phone number, direct phone number, and email are in this paperwork. And if you wanted to make sure that it get, properly authorized work being done, you can give me a call and I can check it out before you okay it. And if there's any questions about the rebates, please give me a call. Is there any other questions that anybody had in regards to the presentation tonight? Yeah. Rick?
Is there any telltale way of knowing that a steam trap is working or not?
Yeah, there is.
Yeah. I mean, I'll tell you, we showed a video to the contractors that's like 17 minutes long. Oh, sorry. Yeah, so the question was, is there any way to tell if a trap has failed or not? And I'll talk about that in a minute, but what I'm going to suggest also is that the video from the contractor's presentation is going to be put online, and you can look at that video. It shows specifically a number of different ways to check and see if a trap has failed or not. But I mean, the main thing is you can kind of listen to it, and it should be cycling on and off like a thermostatic valve, because the bellows should be. You could take a screwdriver and put it up to your ear and put the tip on the valve. You should hear it moving in there. If you hear a rushing sound, that probably means it's failed to open and steam is just rushing by. Also, it depends, if it's cold, if the trap is cold, that probably means it's failed closed and it's full of condensate. So you can kind of look at a number of different things that you can check to see if it's working properly. And also, if the radiator isn't producing very much heat, then that probably means that maybe the trap isn't working properly as well. Any other questions? Yeah,
We rent a business and there is no radiators.
okay,
It's there's a main valve and an apartment valve and then the business valve.
okay,
And the guy said the main valve needs to be all the way open and for our business to get any heat, that second one needs to be open to a portion
okay,
for us to get any heat. How do we know right where to set that? There's no
right.
regulator or
So is it, there's no radiators, you're saying? Is it air handling units? Air,
it's pipes through the walls from what I'm told.
yeah, well, that's I mean, is there like moving air? I mean, warm air blowing out of any vents or anything like that?
In our ceiling, there's
Yeah, so what you have is what's called an air handling unit. So you have a steam to air heat exchanger somewhere in the building, okay? And is that set by a thermostat? Do you have a thermostat for the air to come off and on? Or
Yeah.
Okay, so basically what we talked about is someplace there's an air handling unit that heats your building, and it's the air, when there's a thermostat, calls for temperature. It turns the fan on probably. Now steam, if you keep that valve open, more or less, that means steam is always going to the air handling unit, but it won't condense quickly if there's no air blowing through the air handling unit. So it'll condense slowly, but it should have a trap on it as well, just like a radiator, to work properly. Now, it is possible to retrofit a thing like that with what's called a control valve. So you can put an actually actuated valve, the one that you manually are opening and closing, that itself is set on a thermostat. And that means it'll open up when when steam is called for. I mean, it would require some retrofitting. But the thermostat that turns the fan on can also open that valve. But you have to change that valve from a manual valve to a control valve.
Right, and we have that. We don't have that control as renters.
Right.
So what do we need to do as far as?
Well, I mean, there is a rebate program. I think I would talk to your landlord and say this is, because that's not a very efficient way of doing things. That means that the steam, it's heating the pipes all the time, and it's running through it's being condensed in the air handling unit, even though your thermostat's not calling for heat. So that's wasting energy, basically. So for me, I think the only thing I can think of offhand is to approach the landlord and say, hey, New Ulm Public Utilities has a rebate thing. We think there should be a control valve on that valve that goes off and on with a thermostat.
Yeah, and the gentleman that was there from the city also said that too, and it's just, I can't see paying $600 for steam heat for one long room. And I have a friend in town that has a 3-story house that is electric heat, and his highest bill is $500.
Mm-hmm.
And I understand, it could be more expensive because it was cold and blah, 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 but it just seemed really unfathomable to be almost $600.
Yeah, actually, if you were to compare, I mean, it's worse than that because the cost of steam is much less than electricity in terms of cost of BTUs. So clearly something, if the two buildings were equivalent, there's clearly something wrong going on in your system. And if you're paying the utility bill, I mean, the other side of it is if you could install the control valve yourself,
Yeah.
because it is a fixable thing, and it should. And the other thing I'd want to be sure is that the air handling unit that's serving your building is only serving the part you rent. So you might want to get an HVAC contractor in there and make sure, because who knows where that air handling unit is? You don't know where it's at.
Right.
You don't know where the air vents go from that. It could be heating other parts of the building without your knowledge. So that's also a possibility, and maybe one of the reasons why your bill is higher than maybe you think it should be for that space. So that's something you want to check. In an older building, sometimes all these changes get made, and people forget, where things are going.
Yeah, and I can understand that too, but thanks for the ideas.
Sure. Any other questions? Yeah, that's one thing, I mean, that I wanted to ask you and just touch on briefly, that controlling that main steam line is a good idea. You know, not just cracking it open in the winter and then shutting it off in the summer. It's a good idea to think about, because it adds the level of control. You can put a thermostat somewhere in the interior of the building that would turn the steam on when steam is really called for. And that's something that would make the whole system more efficient. Otherwise, steam is heating the pipes, and even if they're insulated, the steam is condensing inside those pipes all the time because the valve is open all the time. That condensate steam is condensing, you're not getting any really usable heat from it, and it's going down and through the meter and you're paying for it. So that's why it's a good idea to investigate the idea of controlling the main steam line. To shut the steam system off when it's not in use.
I have a question.
Yeah.
Talking about controlling the steam, at the main valve where it comes from the city into the building,
Yes.
in the summer, you turn that off.
If you don't have, the only reason people would leave that on is if they're heating potable water or something like that.
Otherwise, you should turn it off.
Yeah, there's no reason to keep it on because if you leave, the steam system in the summer is energized by the utility because there are people that use it in the summer. But if you have no use for it, you should turn it off because that steam will go up into your system, condense in there, and go through the meter, and
You don't need it.
you don't want it even, you know. So I would turn it off. Okay, well, thanks for your attention, and like I said, if you think of other subjects or questions or things, let Derek know, and we'll try to, you know, I mean, the utility may come back with some additional, and it's also going to be put online, so if you want to look at some of the things.
All three. So this was the third and final class that Carl has done for us. The first was with the Water District Energy Department. That was about a 2.5 hour, 3 hour class. That should be on NewCat YouTube. So if there's other answers maybe that, or questions you had here that weren't answered, that's much more in depth. You know, you can fast forward up and down through that. There also was taped, was for the vendors, was also taped and will also be on YouTube. So if anybody wants to take a look at that and get some other ideas, or if something you forgot from here, you can take a look at that. So, but thank you for all that came. Appreciate it.